Covert Communication, and more specifically Steganography as an example of that. So, okay. I'm Jim. I do like some blue team stuff, red team tool development. Yeah, sorry, I forgot to fix that slide. Okay, so great start. So what are covert communications, right? It's the idea that you can send data back and forth without other people knowing that you're doing it. It's something like encryption is good for like hiding what your data is, right? But people are still going to see, oh, you're sending this secure message. The emphasis on covert here is that like people don't even know there's a conversation happening, which can make it obviously harder to snoop on. There's a billion examples for this. Some like ones that we use for red team might include like packing stuff into certain protocols, because there's a lot of unused flags, unused message fields, all that sort of thing. Something that Ian worked on a little bit was some flashing lights as like a visual thing. So you're looking at different colors of flashing bulbs to send messages. Like that's covert channels. It's hard to describe really, because it's basically just any way of communicating that's not recognizable. And one really cool example of this, or I think it's really cool, is steganography, which is about encoding stuff into images. Yeah, so basically like you can hide pretty much anything in a file, right? A picture could be pictures worth 1,000 words, right? Or, I mean, 8 million pixels, like whatever. A picture can have a lot of stuff in it. So like something that might look like a regular picture can have a lot of information crammed into it. And an easy method for this is called least significant bit stego. And so the general idea is, right, like pictures, each pixel, colors have values, right? Like they're just numbers. And if you change like your red value from 255 down to 253, that's like no noticeable shade difference. The naked eye is like not gonna be able to tell that. Like these two reds, those are actually different colors. They're only different by 2 bits though. So even though you can't tell, right, like we have now effectively gotten like 2 bits worth of information. So if you can cram like a few bits into each pixel, right, and an HD picture has like 1 million pixels in it, then that's a lot of data. So what I'm going to be talking mostly about, because it's like what my project is with PNGs. And there's other types of images that have this as well. But more than just RGB, it's got this alpha field, which is opacity. And unless you change it down really low, you can't really see any difference at all. And I made it a little more extreme in the demo so that we can see a difference. But theoretically, you could probably do like 4 bits without really being able to see the difference. And that's 4 bits per pixel, right? So that adds up quick. So like you can change a little more here than you can change with the colors, and that's going to be useful. So just the general idea is that like you make really small changes to this picture, but you make that really small change to every single pixel. So now that, I don't know if I'm explaining this well, but generally you can encode stuff like, it's really easy to put some text into that. That's pretty trivial. Like I showed before, that's ASCII characters. You can just cram bits into it. So actually just message decryption is pretty easy, or decoding. And some other really cool implementations of this is like video, obviously, right? Because videos have 60 frames per second. Like that's a lot of data, right? Or audio is really similar. Audio is also just bits. I mean, it's all just bits, right? So if you change like 1 bit for each bit of audio, like you're not going to be able to hear any difference. But in a 5-minute song, that's going to be a lot of data. So the little thing that I just whipped up like yesterday / this morning is it reads whatever binary file. So rather than trying to hide like strings or messages, we're going to be hiding files, which is potentially useful for like red team is the idea here, where we can put an executable, like we can decode that into base 64, we can hide that base 64 in the image, and then later on we can take it out and execute it. So I don't actually know if this works. It works like trivially, but yeah, exactly. Demos never work. Is this big enough? Can people see this? Sure, bigger? Okay. Okay, so first we've got the image I'm going to use. I'll talk about the weaknesses in a little bit, but one of the big weaknesses is that since I'm only doing a single picture, right, and I have like a lot of data, this is like a 4K image, which takes a long time, right, and it's, because it's a really large image, so it takes a long time to read and write it. So I would like to transition to video at some point. But this is just like the picture we're going to be encoding to. And we'll do a before and after in a bit so you can actually see the difference. So, nope, not decode. Yikes. Okay, so first actually, we want to look at, what do we want to look at? Oh yeah, so I've got this little implant. This is the thing that we're going to be actually like executing, right? So it's really simple. It's just like a little binary. It's going to like give some output to standard out, and it's going to create some files. So it's a really simple payload. I did that because it's really small. Like it's only a couple megabytes, whereas one of our real implants is going to be like 10 megabytes, and then I would have had to actually implement the video, and that would have been really hard. So we're not doing that. So now we can actually like encode this. I forgot the argument order already. Yeah. So we're going to take our space picture from before. Theoretically, like JPEGs you shouldn't be using because they don't have alpha values. But my program will like add alpha values to them and then turn it into a PNG basically. So you can, yeah, it's a little cheeky, but it gets it done. Okay, nope, that was wrong. And so the output image, we're gonna do a PNG, I guess. Takes a little bit because like I said, it's a really, really big file. Okay, it shouldn't be taking this long. Something bad's happening. That's great. Here we go. Here we go. Let's give it a second. We'll see. We'll see. Okay. Yeah, so that kind of worked. So now, here we go. I don't know if you guys can even, see, I tried to make it like really extreme. Like I'm changing 6 bits, which is a really high number of the alpha value. If we zoom in right here, I guess you guys can't probably see it at all. There's like a color difference line right here, where to the left, it's like it's a little lighter. You probably, maybe the projector's just not that great. But anyway, like I even tried to make this visible, and it's still not very visible, right? And even that, so 2 megabytes, we used about like a third of the image, I would say. Maybe a little less. So that's the idea. And just to show you in like an actual visible way, so this examiner is just going to look at like a few of the pixels and show us the RGBA values. So if we look at the first like 10 pixels, we can see the RGB values. They're all 255 for the A values. But now if we do this thing that we just created, this hacked space, you can see the RGB values are all the same, but now these A values, whereas before they were all 255, now they're different, right? And those differences, each one of those differences is the order of a base64 character, which I'll explain in a little bit. So now we've got like this picture, right, that has this executable stashed in it. So, oh, yeah, sure, I can do that. Yeah, good call. Yeah, so it's pretty similar, actually. Because it went from PNG to, or from JPEG to PNG, so it's a little bigger, I think. I don't actually know. I haven't looked at this. Is that a lot bigger? That's a lot bigger. Yeah. That's substantially bigger. Yeah, okay. Wow, big difference. Okay, big sad. We'll figure that out later. Well, that's just normal file. Yeah. Yeah, so, yeah. Very, very, very true, very true. So now we want to actually decode this, so we're going to take it out of our image, and we're going to make our binary. This part takes the longest, I think. Well, guess not. Cool. All right. Yeah, I have robustly tested this. Yes, definitely. So now just to like show what this actually is. I know theoretically this could be a collision, but I just hope not. Now we're gonna, where was it? Yeah, so ignore that garbage in the middle. But these are, so the hash is the same, right? Even we just extracted it from this image, and now if we run it, it does the same thing as that other binary did, where it's gonna drop some crap and it drops some files there. So theoretically, that could actually be used to like do something cool. The part of this that's actually interesting, which I could not get working, I was working on it until I came up here. I can't get it. But it will be there soon. It actually, the idea is, here we'll go back because we got slides on it. So just dropping a binary on the file is like not very cool, or it's not very useful at least, because now, oh, there's just a binary there. Like, cool, we could put tons of malware places. There's this fantastic syscall that allows you to allocate memory like it's a file. So you get a file pointer to just a block of memory. So yeah, using memfd, you can actually extract that base64 stuff, and rather than writing the file to disk, write the file to memory and then execute it. So that's pretty cool. It was almost working, but not great. And yeah, I really like to do video or like a GIF at least, because that way, GIF. So that way you could, like, we could actually put some real implants in it rather than just a 2 megabyte binary or whatever. So yeah, that's it. Anyone have any questions? Probably not. Oh, yeah.
Why are you using like memfd over just like
I don't know. 5 minutes of Googling told me Golang and MFD was easy. It's not, but it should be. Troy?
have you seen any like real APTs using this kind of?
Yeah, actually, this was in an old, I had a previous version of this presentation where I mentioned that. This was maybe like 2 years ago. There was this, the campaign was called like Skojo or something. It was this really nice picture of Scarlett Johansson that had a malware implant dropped in the back. And yeah, they dropped that on a lot of things. It was like a couple thousand machines, I think. So, like really daily, is it that effective? No. Is it on the attack framework? No. But like, I think it's cool. All right, thanks.
Thank you, Jeff.